Greetings, fellow nerds. In this video, I want to talk about the water you might use in an amateur lab. Without question, water is the most used solvent in all labs, and most amateurs are using municipal tap water as their source. For most amateur experiments, this is perfectly acceptable, but it's not exactly pure water. Tap water tends to have dissolved minerals, mainly calcium and magnesium ions, as well as carbonates, chlorides, and sulfates. Water containing lots of these minerals is sometimes called hard water. If you leave water to evaporate, you can see these minerals left behind. You can also quantify the mineral content with a TDS meter. These minerals are present in all your experiments using water and can present a contamination problem. They can be particularly problematic if you're doing very sensitive work like growing crystals, analytical chemistry, electrochemistry, or just want to isolate pure compounds. So if you want to improve the overall quality and reliability of your experiments, it helps to have water that doesn't have these minerals. At the very least, when you leave your glassware to dry, it won't have those unsightly water spots. Even if you're not an amateur chemist, then purified water is still useful for such purposes as topping up lead-acid batteries, filling CPAP machines, or even just straight drinking if you don't trust your municipal water because it might contain lead, arsenic, or some other contaminant. There are plenty of places in the world where this is a legitimate concern. Another very popular use for purified water is reef-type aquariums that constantly need to replace evaporated water. The minerals would upset the extremely delicate balance of the system, and so any added water must be purified so better control can be maintained. Now, the classic way of getting purified water is to distill it. Distillation works very well for producing mineral-free water, and if you only need a little for the occasional experiment, then it's probably the best option as most amateurs likely already have the distillation equipment. But it's a very energy-intensive process as you need to boil water, which is notorious for requiring lots of heat to do so from the tremendous enthalpy of vaporization. It's also very slow, taking many hours to make a useful amount. Now you can buy distilled water directly from grocery stores, and this is very useful and convenient, but extremely expensive for the amount of water you get. Instead, the modern way, used by professionals, medical industry, and even semiconductor fabs, is to produce deionized water on-site using a reverse osmosis deionization system. I'm going to walk you through one and explain how it works. This video is a little different in that I won't be doing experiments, but I think it will be educational. So this is the system I use in my lab, and as I'm rebuilding my lab, I finally got around to retrieving it from storage. You've never seen it all this time because it's usually bolted to the wall in the back of the lab connected to a water pipe. But since I haven't bolted into my new lab yet, I can show it to you. This model is about 15 years old now, but it still works, so I keep using it. I don't think they sell this particular one anymore, but you can buy modern systems very easily, which are probably cheaper and better. I remember decades ago that these systems were a rarity and distillation was the common method to get purified water. But now it's incredibly easy to buy these, and now I think all amateurs should consider getting one for serious work. Although granted, they are somewhat expensive, so they're probably lower on the list of things to get after hot plates and scales. Anyway, this unit is rated for about 50 gallons of water per day, but I find it only actually produces about half that. Nonetheless, it's good enough for my needs. The basic components are 2 carbon filters, a reverse osmosis membrane, a water storage tank, and deionization resin. Now, the tubing is very confusing since it loops around a lot, so I'm going to show a schematic of how this is hooked up and how it works. The system is connected by a standard hose connection and runs entirely from municipal water pressure. You don't need any extra energy for the system to operate. But some users will add a booster pump to increase the pressure for better efficiency and flow rate. Anyway, the water first passes through a carbon filter to neutralize any chlorine or ozone added to the water and sterilize it. It then goes through a reverse osmosis membrane where it is separated into a permeate water stream with most of the minerals removed, and a wastewater stream where the minerals are concentrated. The wastewater stream is discarded and the permeate water stream goes into a storage tank. The storage tank is under pressure so it can both receive water under pressure and push that water back when the pressure reverses. Now when the water is needed, it goes through another carbon filter to remove some of the leftover contaminants and then through a bed of deionization resin to remove any leftover minerals. The water that exits is fully deionized water. And that's how I get deionized water for my lab. As a side note, in case you're wondering, this valve here turns off the water when the tank is full. This is to save water if it's not being purified. Anyway, that's pretty much how the basic system works. Now I know going through schematics is one thing, but it helps a lot if you can see the actual parts in a real system, so it's a lot less intimidating if and when you purchase your own. Since I need to change all the filters and membranes in mine anyway, I'll show them to you and explain in detail how they work. So first, let's get the input carbon filter, which is contained in this filter housing. As you can see, I'm very weak and flabby, and it takes a few minutes to pry this thing open. Now I drained out as much water as I could, but there's a lot of water remaining, so to contain any spills, I'm doing the disassembly in this plastic container. And there we go. Let me get the filter out. Now this filter is covered in this yellow sediment that came in with the water. It probably contains some rust from the pipes. Anyway, it's very minor, but tap water is rarely perfectly clear. The carbon filter blocks some of the sediment so it accumulates and becomes this yellow coating. Now the carbon filter itself is nothing more than a couple of hollow concentric tubes filled with activated carbon and sealed at both ends. The unit is hollow, but the water actually doesn't filter through the center. Instead, the water fills the housing first, flows to the sides of the porous tube, through the carbon, and into the center bore where it then flows up and out of the housing. It's built this way to give better flow rates than simply packing a tube with carbon and flowing the water through. When replacing the filter, it also helps to clean out the housing, which has accumulated some grime, mineral deposits, and some sediment. I'm going to do that now over the sink and come back. And here we are. And now I'm going to unpack and install the new replacement filter. You can clearly see the difference in sediment accumulation. Now if you live in an area with lots of sediment and you find your system having sediment accumulation problems, you may want to install a particulate pre-filter specifically designed for removing sediment. I don't have one because the sediment problem is very minor where I am. Interesting, this particular one has a mesh at both ends, but it should still work. Oh, by the way, if you're having problems centering the filter so it lines up with the plugs, then it might be helpful to turn the system upside down and standing up the filter. It doesn't always work, but it's an alternative. Okay, let me tighten that back up and the input side is done. Now I'm going to do the output side. Now having a filter on the output side is actually optional, and it's more for removing odors and remaining contaminants that got past the membrane. It's not strictly necessary, and you'll find a few systems that don't have them. But you might be asking why we absolutely have to have an input carbon filter. The primary purpose is to remove reactive chemicals like the chlorine and ozone that's normally added to sterilized tap water. This is critical as reactive chlorine will damage the reverse osmosis membrane, which I'll show in a couple of minutes. Now the carbon filter will also remove some sediment as well as absorb some minerals and organic contaminants. But the primary goal is still removal of the chlorine. Oh, by the way, this is the used output filter. As you can see, it's much cleaner since most of the sediment was already blocked by the input filter. Okay, let me go wash the housing. And we're back again. Anyway, the chlorine removing chemical reaction that happens at the input filter is a combination of catalytic decomposition of the hypochlorite ions as well as direct oxidation of the carbon with hypochlorite. Now we're not actually making carbon monoxide. We're just oxidizing the bulk carbon surface. But the end goal is still the same, to destroy the reactive hypochlorite ions. Eventually though, most of the sites will be used up and the filter will no longer be effective in removing the chlorine, so the filter must be replaced on a regular basis, usually every 6 months or so. Now let's change the reverse osmosis filter. Let me get in there. And here is the reverse osmosis membrane unit. The tube you see here is not actually connected at this side and is simply blocked. Instead, the water flows into these side channels through the unit out to the other side. It's hard to see, but this channel is actually spirally wound. While the input water travels straight down the unit and becomes wastewater, the permeate water travels inside the spirally wound membrane envelope until it reaches the center output tube. On the other side, the wastewater exits the channel while the permeate water exits through the center tube. Oh, by the way, the black ring is a sealing ring to keep the input water on this side and prevent it from traveling around the unit into the wastewater side. So do not remove the ring even though it's very easy to do so. Okay, so what's happening when the membrane separates water? Now I'm going to skip the video ahead to where I take apart the used reverse osmosis membrane unit so you can get a better sense of its construction. It's a rolled up multi-layer device. First, I'm going to take off the sealing ring. Occasionally, people take it off thinking it's part of the packaging. I repeat that during normal operation you do not take off the sealing ring. I'm doing it now because we want to take it apart. Now let me take apart the covering. And there we go. And as you can see, we have a rolled up membrane. This is done to maximize available surface area as the osmosis and reverse osmosis effect actually proceeds at an incredibly low rate proportional to surface area. So by using a huge surface, we can get a barely acceptable rate. Now this large coarse plastic mesh is a separator, so the input water has space to flow over the membrane. The membrane is the tan envelope I'm unrolling, and it's connected to the output tube on one end over here. Now let's have a look at the membrane envelope. It's 3 layers. The 2 outer layers are the actual polyimide reverse osmosis membranes. The inner layer here is actually a very fine plastic mesh that separates the membranes, allowing the inner permeate water to flow between the 2 layers toward the center tube. It's sealed at the edges and also at this join line here to prevent the permeate water and the wastewater from mixing. The water inside the envelope can therefore only flow toward the center tube where it's collected and exits. So to recap, now that you know where everything is, the input water flows over the reverse osmosis membrane under pressure. The pure permeate water is forced through the membrane and ends up inside the 2 membrane layers. With nowhere to go, it moves toward the center tube and exits. Meanwhile, the minerals are left behind and travel with the leftover wastewater and exit out the other end of the membrane. So that's what's happening, but how exactly does it work? It has to do with the process of osmosis. Basically, if you have 2 reservoirs of water with different concentrations of dissolved solutes and separate them by a semi-permeable membrane that passes just a solvent, over time the solvent water molecules will diffuse between the 2 reservoirs until the concentrations equal. The membrane is the key. It's semi-permeable and behaves like it has molecular-sized pores that allow the passage of uncharged small molecules like water and resist the passage of large or charged molecules like salt. Now the amazing thing about the osmotic process, or amazing to me anyway as a chemist, is that this process is accompanied by a change in energy. The resulting equalized system is at a lower overall energy than the unequal system. This energy comes out as osmotic pressure. As the solvent flows toward the highly concentrated side, the pressure of that reservoir increases. We can actually run an experiment to show the process. Here I've cut out 1 layer of the reverse osmosis membrane and I'm folding it into a very crude filter. Now I'm going to place it into a beaker of clean water, and on top I'm going to add some salt water as well as a few large chunks of salt. Now the bottom has to be immersed in the water below or this won't work. We need to be able to flow back and forth. Let me adjust the camera. Now normally gravity would push the salt water downward through the filter where it mixes with whatever fluid is at the bottom. But this is a semi-permeable membrane that allows water to pass through, but not salt. So let's begin the time lapse. And there we go. The water is actually flowing backwards. Osmotic pressure forces the water to flow upward and dilute the salt water. The energy produced by that process is enough to overcome gravity. Now the cool thing about energy producing processes is that if you can force the energy back in, then you can reverse the process. And we do that by applying an external pressure to reverse the osmotic process. And that's where the name of reverse osmosis comes from. Reversing the osmotic process allows us to take water out of an already concentrated reservoir and put it into a less concentrated one. In our system, the water pressure of the incoming water itself is our source of energy and forces water through the membrane. Now if you're paying close attention, you might be wondering why I said that the membrane can resist passing charged ions. A single atom sodium ion surely can't be that much bigger than a water molecule of 3 atoms. So what's happening? The reason why charged ions tend to behave like they're larger despite perhaps having less atoms is because the charge gives the ion an electric field that attracts solvent molecules and creates solvation shells. Pushing through a membrane requires breaking up the shell, and this is energetically unfavorable. So it behaves like it's too big to fit through. Kind of like how a famous celebrity being mobbed by fans has a very hard time getting through the door despite being perfectly able to fit through. The fans make the celebrity effectively much larger than they physically are. Interestingly, we can engineer membranes with differing effective pore sizes and select the cutoff for what we want to pass. For example, dialysis tubing can be made to pass both water and salt, but block large proteins. But I digress. Let's go back in time again, and now I'll replace the reverse osmosis membrane with a new one. There's actually no need to remove the label because all of the pure permeate water is in the center tube. The label is on the side where the wastewater is, so it doesn't matter if the glues and dyes contaminate it. For best performance, the membrane should be changed out every couple of years. Now when you go out and buy a membrane, you'll find the market is dominated by polyimide membranes that are called thin film composite membranes, or TFC membranes. And that's what I use in my system. But occasionally you may encounter a rarer membrane type called a cellulose triacetate membrane, or CTA membrane. They're made of different materials, with polyimide being a synthetic plastic, while cellulose triacetate is a highly treated paper product. The practical difference is that TFC membranes are destroyed by chlorine and so must have chlorine removed with a carbon pre-filter, as we've been doing so far. CTA membranes, on the other hand, are actually decomposed by bacteria and fungus but resistant to chlorine, so you actually want to pump chlorinated water across them. This eliminates the need for a carbon filter. The reason why polyimide-based TFC membranes dominate is because of the output water quality. TFC membranes remove more minerals than CTA membranes. The estimates vary a lot, probably due to marketing hype, but TFC membranes are advertised as removing around 95 to 98% or so of the minerals, while the CTA membranes remove about 85 to 95%. Personally, I find practical rates to be lower, but TFC membranes are still better than CTA membranes. While the numbers seem similar on paper, it's actually a dramatic improvement. A CTA membrane that retains 15% of the minerals is actually performing 3 times worse than a TFC membrane that retains 5% of the minerals. This means you need 3 times more deionization resin downstream to process the same amount of water. So most of the industry has moved to using polyimide TFC membranes despite the requirement of a chlorine-removing pre-filter. Some specialized applications where chlorine must be kept may use CTA membranes. But as an amateur, I say stick with the more common industry standard TFC membranes. Because they're so ubiquitous, they're also much easier to find and tend to be cheaper than CTA membranes. Anyway, once we're past the membrane and past the carbon post-filter, the water passes through a column of deionization resin. I had already changed this before I decided to make a video, but I'll still show it and explain how it works. The housing is actually the same as the carbon filter housing, but I selected a clear one so I could see the resin. The resin itself is contained inside this cartridge, and unlike the carbon filter, this one flows bottom to top rather than outside to inside. We want the water to flow this way to ensure that the water flows through the most possible resin to make sure it removes absolutely all remaining ions. So how does it do that? The resin is an amazing product all by itself. It's a special type of plastic that's made of monomers with functional groups that give the plastic an ionic charge. So it will actually absorb and hold ions of the opposite charge. I might make a video someday on ion exchange resins since they're so fascinating. Anyway, this resin is actually a mixture of 2 resins, a cationic exchange resin and an anionic exchange resin. You can see them here manufactured into beads. The green ones are the anionic exchange resin, while the yellow-orange ones are the cationic exchange resin. The cationic exchange resin removes positively charged ions and replaces them with hydronium ions, while the anionic exchange resin replaces the negatively charged ions with hydroxide ions. These ions neutralize each other, and so you get deionized water. This brings down the ion or mineral concentration down to nearly 0. And as good as distilled water for almost every purpose. In case you're wondering, we don't make beads containing both resins at once because if they're physically mixed together, then they'll neutralize each other and be useless. So we make separate beads that can only interact through the water. Now the reason why we need the deionization column is because the reverse osmosis membrane is not perfect. It removes most of the minerals, but a small amount will still pass through. The deionization resin serves as a final scrubbing or polishing step to remove whatever the membrane missed. At this point you might be asking, why not just use the resin by itself and skip all this complicated and expensive pre-treatment with carbon filters and reverse osmosis membranes? Why not just pass the water directly through the resin to deionize it? Would that work? Actually, in fact it does. And you can actually purchase such systems that work on exactly that principle. The reason why the vast majority of systems include the reverse osmosis system is because of capacity. The deionization resin has an extremely limited capacity. Once all the ions preloaded into the resin are swapped out, the resin is spent. The amount in here can only process maybe 10 to 20 grams of minerals, so it can only deionize a few hundred liters of tap water before it needs to be replaced. Unless you want to change the resin every week, this is totally impractical and very expensive if you don't regenerate the resin. But the reverse osmosis system removes around 90% of the minerals. With only 1/10 of the minerals remaining, the deionization resin effectively handles 10 times more water. So you can get thousands of liters of water between resin changes. Also, the recurring costs of the reverse osmosis system is less than the cost of more frequent resin changes. Also, deionization resin only removes ions. It doesn't remove particles like bacteria or viruses. So if you're using your water for drinking or other biological endpoints, then removing them with a reverse osmosis system is preferable. Now the resin I have here includes the useful property of being an indicator resin. This resin type is optional and non-indicating resin is cheaper, but indicating resin has the advantage that as it absorbs minerals, it will change color. We can demonstrate it by spreading out the resin in this dish with some water and placing a salt chunk in it. As the salt dissolves, it exchanges ions with the resin and changes color. Now only the anionic exchange resin has an indicator in it, giving it this blue-green color. The cationic exchange resin does not and remains orange color whether it has minerals or not. There is no real need to have both unless you have extremely unusual water that has mostly cationic contamination. In that case, you can indeed purchase resin that contains a cationic indicator. Now the point of using indicator resin along with a clear housing as I have, is that as the resin is depleted of its deionizing properties, it will change color and the color change will move up the cartridge. I can directly see when the resin needs to be changed rather than having to measure the water quality to make sure. But if you're using regular resin, then you can monitor the output quality using something called a TDS meter for total dissolved solids. In actuality, this is really measuring conductance and converts the value to the equivalent level for sodium chloride. So it's not actually analytically valid. Nonetheless, it's still a useful relative measure for comparing changes in the same system. Here I have 3 beakers with 3 samples of water. On the left here is water directly from the tap. The middle is water just after the reverse osmosis membrane treatment, and the final beaker is the water after deionization. I already have the meter immersed in tap water, and it contains 276 to 277 parts per million of minerals. Let me get that out and wash the meter with some deionized water first. Now the reverse osmosis treated water contains 29 parts per million of minerals. As you can see, much better than straight tap water. Finally, the deionized water has 0 parts per million of minerals. Although it's more likely that there are still some and they're simply below the detection limit of the TDS meter. The true value may be 0.5 parts per million or less. But you can see we can have dramatically improved water quality using a reverse osmosis deionization system. Anyway, if the resin is depleted, then the TDS reading will start to rise. You should change your resin at that point. Periodic monitoring of the TDS readings also helps you notice if something might be failing prematurely by a dramatic change in TDS values. For example, if the reverse osmosis membrane fails, then the reading on the reverse osmosis water might spike beyond normal. At that point, you would change both the reverse osmosis membrane and the carbon prefilter. Now, if you don't have a TDS or conductance meter, then an alternative chemical method to crudely determine water quality is to add a few drops of saturated silver nitrate solution to a sample of water. Chloride ions react with the silver ions to make insoluble silver chloride that would turn the water cloudy. Since chloride ions are present in most impure sources of water, Detecting them after deionization shows that they got through the system and that the deionization resin should be changed. Granted though, it's a very crude test and not very sensitive. Here I'm testing some reverse osmosis water before deionization. As you can see, the cloudiness is there, but it's barely visible. A TDS meter is much more sensitive, so I recommend getting a TDS meter if you can. They are very ubiquitous and much easier to get than silver nitrate. Now at this point you might be wondering if the resin merely exchanges ions and is not actually damaged or consumed, then would it be possible to exchange the ions back and regenerate the resin? Actually you can. And I'll see if I can make a video on regenerating depleted deionization resin. After all, as chemists, we should take advantage of the few times when we know what we're doing. Now you might be asking if a water softener system that uses ion exchange resin would already be producing good water. Water softeners use the resin to replace the magnesium and calcium ions with sodium ions. While this water is good for cooking, washing, and bathing, for chemistry purposes it's still mineral-containing water. So water softeners are not a substitute for a proper reverse osmosis deionization system. But interestingly enough, there is a special case where they are used with a reverse osmosis deionization system. If the input feed water is extremely hard and has a nearly saturated level of minerals, then those minerals can actually precipitate out onto the inside of the membrane as the membrane removes the permeate water and concentrates the minerals past saturation. This clogged membrane stops separating the water and you get tremendous wastage. Purified water output will slow and can even stop. The solution to this is to pre-treat the input water with a water softener. Sodium salts have a much higher solubility than calcium and magnesium salts, so they can be concentrated much higher before saturating. Softened water can go through reverse osmosis without any danger of precipitating onto the membrane. So if you notice your membrane working at first, but then start wasting tremendous amounts of water, and if you have very high TDS readings on your tap water, then maybe it's hard water precipitating onto your membrane. A water softener before your reverse osmosis deionization system may fix the problem. Professional systems sometimes add hydrochloric acid directly to the water to dissolve any hard water scale, but that requires precise monitoring and control and is beyond the scope of the amateur. Now before I go, I want to share a few thoughts on the limits of the system and whether this is actually good water in the absolute sense. For amateur purposes, this is excellent. Probably the most cost-effective water for the purity level obtained. For professional, analytical, or research purposes, this is still crap. For that sort of work you need even lower TDS readings, and in fact you stop using the TDS measurements since we're already past the lower limit. Instead, we measure raw conductance directly, which detects much lower levels of contaminants. And something I glossed over is that high-quality water should have very low organic compounds, something which we can't even detect without specialized and very expensive analyzers. As amateurs, we don't bother since the levels in tap water are too low to affect amateur work, but for professionals, organic compounds can be a problem. This system, as good as it is, isn't really designed to remove all organics. The reverse osmosis membrane will remove a lot, but small uncharged molecules will pass through. If I put alcohol into the water, a fair amount would actually end up on the purified water side. The carbon filters will remove some, but even they have limits. And there will always be some microscopic holes in the reverse osmosis membrane that let through a tiny percentage of larger molecules. Professional systems use additional carbon filters and specialized reactive filter media to absorb or destroy organics. A very common active method is for water to be exposed to extremely powerful sterilizing UV light. The light generates free radicals in the water that destroys organics, or at least converts them to their charged or polar products. These products are much easier to remove than the original organics themselves. But now the water needs to be purified again to remove those organic waste products. Very expensive professional systems have multiple stages and high-quality components to rigorously raise the quality of water orders of magnitude higher than a consumer system. A further complication as you approach extreme purity, contaminants in the system itself start to become bigger and bigger problems. Particles in the carbon filters get dislodged, contaminants in the plastic or metal components of the housing and tubes leach out, impurities in the resins seep out, tiny amounts of metals and organic residues leach out of the very containers you store the water in, And even the very air itself becomes a contaminant as carbon dioxide dissolves in the water and changes the conductivity. So ultra high quality water is actually not that easy to get. But for amateurs, the water from a consumer level system is excellent. Professional grade water is completely pointless for an amateur where there are already numerous other and greater sources of contamination and impurities. For us, this water is already at maximum level. Now the question comes up a lot of whether distilled water or reverse osmosis deionized water is better. Unfortunately, I have to give the worst answer of them all: it depends. And there is a lot of overlap between them. Ultimately, what you use will depend on your final application and the quality and cost you'll accept. Generally speaking though, reverse osmosis by itself without any further treatment or deionization is considered a lower grade than even crudely distilled water. Reverse osmosis is great for upgrading straight tap water or untreated water and preparing it for feeding into more advanced systems. But by itself, it doesn't remove minerals as effectively as distillation and only partially removes organic compounds. Distillation is very good at removing minerals, but it might surprise you to learn that distillation sometimes doesn't remove all minerals. This is because as the water boils, it aerosolizes some of the contaminants into droplets, which can then be blown over to the purified water side. Additionally, distillation does pretty well for removing large or non-volatile organics, but very poorly against volatile organics. In fact, very volatile organics are barely removed at all as they boil with the water. An interesting problem is that you can actually end up with more volatile organics than you started with because the boiling heat decomposes some less volatile organics. Now, fractional distillation may help in separating the volatile contaminants, but fractionation is extremely slow as to be impractical for the production of bulk purified water. Fortunately for the amateur, the organics in tap water are already extremely low, so distillation alone is sufficient to produce amateur quality water, removing the bulk of the minerals in a single step. This is why I said earlier that for very small scales, you might just be better off making your own distilled water since amateur labs tend to already have distillation equipment. But for greater amounts, the throughput of reverse osmosis-based systems is advantageous, and when you add carbon filters and deionization resin, the quality goes back to competing with distillation. It's when you get into the professional systems that things start to overlap between reverse osmosis deionized and distilled. Professional units superheat the steam to prevent aerosolization transfer, and use multiple stages to successively make pure and pure distilled water. Then they treat the distilled water with carbon post filters to remove organics, and additional filters to capture or destroy anything else that may have slipped past. At that point, the quality more or less overlaps with deionized water, and the differences really come down to the specific design and implementation rather than theoretical rules. You need to actually test the water quality and make the determination yourself if a particular system is suitable to your needs. But for cost and throughput, the reverse osmosis deionization system tends to win out. Now finally, I should cover wastewater and efficiency. Household reverse osmosis deionization systems produce a tremendous amount of wastewater. Exact numbers vary, but for every unit of purified water produced, the system will generally discard 3 to 10 times as much water as waste. That's an efficiency of 25 to just 10%. Now water tends to be much cheaper than electricity, so the overall recurring cost is still much lower than distillation. But if water is very valuable for you, like you're living off-grid and obtain your water from a limited source like rainwater or a well, then maybe you have no choice and must use distillation. A good distillation system wastes only a negligible amount of water. Reverse osmosis efficiency can be improved by reusing the wastewater in another reverse osmosis unit and feeding the permeate water back into the original system. Eventually, the mineral concentration will be too high to separate, but multi-stage reverse osmosis systems can still obtain high efficiencies of 80%. However, that's a big project beyond the scope of us amateurs. Personally, I don't worry about the wastewater. But you might be asking if the wastewater from the system can be used for anything other than dumping down the drain. First, I would not drink it. If you do not trust your water to drink directly, you should not be drinking water where the contaminants are concentrated. I know that should be obvious, but recent world events have convinced me that even the obvious may need to be stated. If your tap water is trustworthy, then you should be drinking that rather than the untrustworthy waste product from a machine not maintained by a professional nor certified by a proper lab. But aside from drinking, reverse osmosis wastewater is still good water and can be used for many of the same applications as the original tap water. One common use is to water a garden or plants with it, as the minerals are actually quite beneficial. More sophisticated users will plumb the wastewater for grey water uses like flushing toilets or even doing laundry. But the vast majority of individuals will simply discard it. So that is how a reverse osmosis deionization system works. A very useful piece of equipment for the amateur that produces water orders of magnitude better than municipal tap water, and now really easy to purchase in the modern era. Thanks for watching. And thanks for supporting my videos through Patreon. I'll admit these past couple of months have hit me very hard and I'm still crawling around. But it's your support that keeps me going. Thanks.